Hello. So now we want to look at the code that I've given you for animating a spring. So let me hide my little picture here. And here's the MATLAB code that you should have downloaded from Google Classroom. Hopefully you were able to successfully get it into MATLAB. So it's not a very long piece of code. And so let's talk our way through it. Okay. First of all, make sure you know this is called Spring Student. This is the version I give to you. You're supposed to update that title and update your comments as we add more things to the code. So make sure you do those things. And let's see what this code is actually doing. Okay, so we have our parameters. I probably could have gotten rid of a few of these lines of space. Let's run it first to see what it looks like. And then we can talk about it. So when I run this code right now, you can see we have an animated picture on the left of a mass on a spring that's simply bouncing up and down. Okay, and so it's oscillating around an equilibrium height. Okay, so as it oscillates, we can see a graph of height versus time. So that's what this simple version does. And as we move along with this over the next couple of weeks, we're going to add more and more to it. We're going to add velocity time, acceleration time. We're going to look at energy over time. And we'll add other things like damping so that the oscillations can die down over time, which is what will happen in the real world. And we'll look at all the different types of damping. Right? But in order to look at this, here we have our parameters. I think you can understand dt is our time step and our maximum time. You can see how that corresponds to how far the time graph went out. This is the mass. Okay. Now take note that 0.6 kilograms is the same as 600 grams. So later on when you're doing problems, I may try to trip you up. If it's in grams, you need to convert 2 kilograms to do the physics, all right? Or in physics, we have the MKS system. So if we want everything to work, you need your mass in kilograms. Here is our spring constant in newtons per meter, as we discussed in class. Now this is the rest length of the spring, okay? So right now it is given a rest length of 15 centimeters, so 0.15 meters and 15 centimeters will correspond. So often in problems in the textbook or that I might give you, lengths might be given in centimeters, and you need to make sure that you convert those into meters so that everything will agree, all right? The top is 1 meter up, all right? The x naught, okay, that's how far the initial displacement from equilibrium, okay? So that will correspond to the amplitude of our motion, okay? So we started 0.2 meters away from equilibrium, and we didn't program in equilibrium. I'll tell you how we're going to get that later. That's going to be derived from the mass, the rest length, and the spring constant. But this will tell us how far the oscillations start above equilibrium for now. We have no initial velocity. We'll change that in a as we move along later. We'll be able to start in different places with different speeds, but for now that's set to 0. You know what g is. Okay, and show solution. This is our theoretical solution. So if I run the code with that on, you see the black dashed line. That's mathematically what we derived in class to be the solution for a vertically oscillating mass on a spring. Okay, it's a simple cosine curve. If I make that a 0, like making it false, you don't see the solution ahead of time. So we're just using a time step loop to predict to show where it will be, and we're plotting that out as we go. So we can compare the motion using a time step loop to the theoretical mathematical solutions we'll come up with, and that's what show solution allows us to do. Plot choice for right now, the only choice we have is height versus time, so we'll leave that on 1, but you're going to be adding plot choices as you go. All right, now let's look at this, line 27. I'm calling this omega 0, okay? or it looks like a W0 because we don't have an omega in MATLAB. So I use W instead of omega. The 0 indicates that that's going to be the zero damping case. When there's no damping, meaning there's nothing slowing it down, the mass down, we'll have omega 0. We're going to need that because later on we're going to have an omega that is for when there is damping. So omega 0 is a square root of k over m. You've seen that formula when we did the derivation of the motion. Okay. Now, stretch EQ tells us how far the spring should stretch to reach equilibrium. Okay. In the previous video, that would have been XEQ. Okay. So we can figure out how far it will stretch to equilibrium by basically we're setting mg equal to kx. And if you divide mg by k, that will tell you how much stretch you have. Okay, so that's based on what you just saw in the last video. You'll be using this to compute where equilibrium is on a couple problems in tonight's homework. Okay, now where will the equilibrium height be? What we do is we take our top height. The spring, even if it had no mass on it, would have its bottom at L0 below the top. But then when we hang a mass on it, it stretches further. So this would relate to the previous video where you would take whatever the top is minus L0 minus XEQ, which we're calling stretch EQ. So because of the mass on the spring, it stretches further, and that tells us where the equilibrium height will be. Okay, and then we'd have a skip command. You've seen these before. So the skip will keep this from the plotting from taking too long. So we can have high precision calculations without the plot taking too long. All right, here we make a time vector in line 32, and line 33 tells us how many times we're going to have for our plotting loop. Now notice line 36. This is the mathematical solution. Okay, the amplitude of the motion is the initial displacement in this for now. So you'll remember we had a cosine omega t plus YEQ, but this is just the initial x instead. Okay, moving on down. We're going to eventually have position, velocity, and acceleration. So those have all been zeroed out for now. And y1 equals YEQ plus x0. That tells us where the height we're starting at. So the equilibrium height plus whatever that initial amplitude was that was given. And later on, so v1 will equal the initial velocity. So we set that as well. For now, that's 0. Okay, and then we get into a loop of the motion. Okay, so you'll remember faves. We start with by calculating the force. It's right here. Okay, and then we use the force to get acceleration. We simply use Newton's second law and divide the force by mass, and that gives us the acceleration. Now I did something strange here. I probably in the future maybe should go back and change that. I start my time step loop at 2 and go all the way out to nt. So you'll notice that this first force that's calculated is the IT minus 1. That will work because we started with a 2 here. If I had started with a 1 here, I couldn't do IT minus 1 because there's no such thing as the 0th y value. So this will give me a force value based on the initial y position. And that value will be used to get an acceleration value. And then in the Verlet loop, we find a middle velocity right at the middle of the interval by taking, notice right here, we took a half time step. And so that gives us a middle velocity. And then we use the middle velocity to take our time step to get the next position. So this line 55 gives me the next position from the previous position and the middle velocity times time. Okay. Then what we do is we recalculate the force in the Verlet method. So we're going to calculate the force again at sort of the right-hand side of the interval. recalculate the acceleration, and then take another half step of velocity. So remember, what was unique to Verlet is you take 2 half steps for velocity, which means you're not really, you're able to do more of a trapezoidal sort of middle sum rather than trying to do everything from a left sum. You get better answers with fewer iterations of the loop. Okay, so a little bit complicated, but you go from force to acceleration to velocity to position, and you just do a second half step to get to the velocity that you have at the end, and then you go back, you just repeat that over and over again. Okay, that's where all of the calculations for the spring position will be. You're simply repeatedly using F equals negative kx, okay? But notice there's not an x here. Like in the previous video, the amount of stretch from equilibrium is the current y position minus the equilibrium position. That tells you how much the spring is stretched. So we're using F equals negative kx, and then we get the acceleration simply by dividing by m, and velocity from the acceleration, and position from velocity, like we've been doing all along. So really the only thing that's unique to this code is that we're using the elastic force now instead of other forces that we have in the past. Okay, now we're ready to plot this. And we do this in, notice there are 2 things being plotted. So we have subplots, 1, 2, 1. Remember the 1, 2 right here tells me we're setting up our plots in a 1 by 2 matrix, which means 1 row and 2 columns. So we have 2 figures side by side. And we're first going to look at figure 1. Okay. Now, figure 1, remember, if we run this, it's the animation. All right. And the only thing that happens in this code, in this program, looks like we call this thing called vertical spring plotter F. All right. Now, vertical spring plotter F is not a MATLAB function. It's a function that I've created that you had to download as well. I don't want to spend too much time going into what this is doing, okay? But this basically is giving us one picture, okay? When we put a y value in and tell where the top of the spring is, this will draw the zigzag spring, okay? Now notice as the program ran, the spring stretches out and then recompresses. So all of the little points along the edge of the spring are going up and down. And so most of the code for vertical spring plotter is locating the points on the edges of the spring. Okay, so you don't need to know what it does in too much detail. We're basically creating a bunch of y values where the points can be, and it stretches them, those points out from the top to the bottom of the spring in equal increments, and then it just plots little connecting lines in black for all of those points. Okay, and so as those points change as the spring stretches and compresses, and it gives a nice little visual effect. This patch command is what plots the green box. Okay, so it's we're connecting those x values to these y values to create the rectangle itself, and then this little bit of code right here is what chooses the color of the box. Okay, so you don't need to know the details, you just need to understand the vertical spring plotter plots one picture. Okay, and notice it's in this for loop. So each time we step through the for loop, the position, the y position changes slightly, and that's how we get the animated box going up and down and the spring compressing and stretching out using the little bit of code in vertical spring plotter. The other plot is more similar to the ones you've done in the past. It's just in the second position. Okay, so this is our height versus time, and that's a more straightforward plot statement. The first line is the blue line. That's plotting the growing motion as the spring goes up and down. IT gets bigger and bigger, and it's plotting more and more of the height versus time graph. that the spring follows based on Newton's second law. And then the second line is putting a blue circle on the endpoint. And then the third line of the plot is taking the leftmost and rightmost x values and the height at equilibrium and plotting our dashed black line for equilibrium. We have our axis command, okay? And then here, you'll notice if we want to show the solution, then it will add another line to the plot. And there's a hold on and a hold off. Those actually could probably be inside of the if, the little if command here. Probably would have been more efficient if I put hold on and hold off inside of that. So they only would happen if we're going to show the solution. So this isn't the most efficient, as efficient as it could be, but it's pretty close. Then there's a pause command in here, and this is to make the animation happen in something that looks like real time. We can change if we wanted to go faster. Back in the parameters, we could change how fast skip was happening, and we can make this thing speed up or slow down. We could change this number here as well if it's taking too long. Okay, so all of those things are what's going on in the code. Okay, and that's how we get to see this spring moving up and down. So as we move forward, you're going to make alterations in this basic code to do more and more complicated things over the next couple of weeks. All right, well, enjoy working with this MATLAB program.